Hello and welcome to Mech Zone. In the previous lecture, we have started off with the chapter on links and mechanism, and we have already discussed the Kurzbach equation, which was given for the 2D planar mechanisms to find out the degree of freedom. And we also discussed that for the different values of degree of freedom, the given mechanism can be a frame or a structure, or it can be a superstructure, it can be a constrained chain, or it can be a kinematic chain, or it can also be an unconstrained chain. Okay, now from this lecture onward we shall start discussing from that point, and we see that if a spring is used as a link, is used, then for example this is a spring, then we would replace this spring by means of two links. So actually this spring is equivalent to two links, so equivalent to two links. So whenever you find a spring attached in any of the mechanisms, then that spring is actually equivalent to two links. Now we will discuss the Grubler's criterion or Grubler's equation. Now according to the Grubler equation, for those mechanisms where degree of freedom is 1 and number of higher pairs are 0. So Grubler actually assumed that for 1 degree of freedom and 0 number of higher pairs, what he did was f is equals to 3 into L minus 1 minus 2j minus h. In the Kurzbach equation he actually modified it, and since h was 0, so this part becomes 0, and degree of freedom to be 1 is equals to 3 into L minus 1 minus 2j, so this can be 3L minus 3 minus 2j. Okay, so is equals to 1, so 3L minus 2j minus 4 would be equals to 0. Now we will analyze this equation. For this part to be 0, 3L, 2J and minus 4. Now we see that this part is even, this part is also even, so this entire part also has to be an even value. Therefore L should always be an even. According to the Grubler's equation, L should always be even number. So the minimum amount of L which is required to form a mechanism becomes 4. So the number of links, minimum number of links to form a mechanism is actually coming out to be 4, and hence L is always even. Now we will discuss about the first mechanism with the lower pair, and that is why it is also called as a simple mechanism, because it is the first one. So we will discuss first mechanism with lower pair, and this is also called as the simple mechanism. Okay, so this is also called as the simple mechanism. So the first mechanism that we would study about is the 4-bar mechanism. Or this is also called as the Quadric cycle mechanism. Here we will have 4 links and plus 4 turning pairs. So in the 4-bar mechanism we are actually having the 4 links in total. Out of those there are 4 turning pairs and there is no sliding pair. So if we draw the diagram of this 4-bar mechanism, okay, this link is actually fixed because one of the links has to be fixed so as to make it as a mechanism. 1, 2, 3, 4. Okay, now this is called as the input link, this is called as the output link, this link is called as the coupler or coupling rod, whereas this portion is actually the fixed portion. and we see that the best position for any mechanism is the fixed position. The best position is actually the fixed position because it governs both input and output. The input and the output both can be governed by the fixed position because it governs both input and output. The both input and output are governed by the fixed position, and hence it is the best position. Now corresponding to the input and output links, we have two types of links which are possible. One type of links are those which are undergoing complete rotation. So the links which are undergoing complete rotation are called as cranks. Those which are undergoing complete rotation are called as cranks, and input and output links can both be crank. They can both be made as the crank. And the second type of links are those which are undergoing a partial rotation. They are undergoing a partial rotation, and these links are called as rocker, or they are also called as lever. So partial rotation simply means they are actually undergoing oscillation. So those which are undergoing complete rotation, they are called as cranks, and those which are undergoing partial rotation, they are called as crank or levers. Now we come to a very important word, that is inversion. Inversion simply means the mechanisms which are obtained by fixing one by one the different links. In a mechanism, if we are fixing one link at a time, whereas the other links are free, then we are going to obtain the inversions of the mechanism. So what happens in case of inversion? Different links are fixed. Different links are fixed one at a time. This process is called as inversion. Okay. Now, if the number of links are L, then the number of inversions are actually less than or equal to L. You have to remember this data, that if we are having the number of links as L, then the number of inversions are always less than or equal to L. Now we will discuss about the inversions of the quadric cycle mechanism. The first one is called as the double crank mechanism. The second one is the crank rocker mechanism. The third one is called as the double rocker mechanism. Okay. So these are the three inversions which are obtained from the quadric cycle mechanism inversion. Okay. Now before discussing about the various inversions of this quadric cycle, we shall first discuss about the Grashoff's law. Grashoff's law. Now Grashoff's law states that for continuous relative motion between the number of links in a 4-bar mechanism, the summation of the length of the shortest side and the longest side should not be greater than, it should be less than or equal to the summation of the length of the other two links. For example, if the length of the smallest link is S and the length of the largest link is L, then S plus L should always be less than or equal to P plus Q in order to have continuous relative motion. So for continuous relative motion between any number of links in a 4-bar mechanism, not for any number of links, for 4 number of links in a 4-bar mechanism, the summation of the smallest and the longest should always be less than or equal to the summation of the lengths of the other two sides. So before going to solve any of the questions, we first have to be focused on this law. If this law is satisfied, then only we are going to move further. Okay. Now we have already seen that the best position is actually the position which is fixed. So Best position is the fixed position, and fixed can be either in the input or the output link. Now, and the coupler position is the worst position. The coupler is the worst position. So fixed position is the best position and the coupler position is the worst position, and coupler is that link which is the once again, okay, coupler is the link which is having the first position, and the fixed position is the best position. And best link for rotation, best link for rotation is actually the smallest link, because the smallest link can undergo complete rotation. Smallest link is the best suited for complete rotation. So first of all, we have to see whether the Grashoff's law is satisfied or not. Now, this law has two conditions. The first condition is S plus L is less than P plus Q. If this is holding, then we would move further. And there are three sub conditions. The first sub condition is if S is fixed. If S is the smallest link, and smallest link can undergo complete rotation, and fixed is the best position. So actually the combo is also the best, and hence it will form a double crank mechanism. It will form a double crank mechanism. The second condition is link adjacent to S is fixed. Link adjacent to S is fixed. If the link adjacent to the S is fixed, then it becomes a crank rocker mechanism. It becomes a crank rocker mechanism. And the third is S becomes the coupler. That means if the link opposite to the shortest link is fixed, then what will happen? S becomes the coupler, and we know that the coupler is the worst position. So it actually becomes a double rocker, or it is sometimes called as rocker-rocker mechanism. Okay. So if the smallest link is fixed, it becomes the double crank. If the link adjacent to the smallest link is fixed, it becomes the crank rocker. And if the smallest link becomes the coupler, or when the link opposite to the or when the S, that is the smallest link, becomes the coupler, then we are going to have the double rocker. I actually told you wrong, that if the link opposite to the shortest link is fixed, that means S is actually, yes, actually I was correct, that if the link which is opposite to the shortest link is fixed, then it becomes a double rocker mechanism. If the S is fixed, it becomes a double crank mechanism. If the link adjacent to the smallest link is fixed, it becomes the crank rocker. And when the S becomes a coupler, then it will form a double rocker mechanism. Okay. Now, first case we have discussed when S plus L is less than P plus Q. Next case we will discuss when S plus L is equal to P plus Q. Now, S plus L is less than or equal to, equal to P plus Q. That means pairs are having equal length. Pairs are having equal length. For example, 2, 2, 5, 5. This is S, this is also S, this is L, and this is L. Okay. The first inversion we will obtain is the parallelogram linkage. Parallelogram linkage. And in the parallelogram linkage, this is the smallest link, this is the largest link. If the smallest link is fixed, then we will obtain double crank mechanism, or it is called as crank mechanism or double crank mechanism. If the longest link is also fixed, we will still obtain the double crank mechanism. Double crank mechanism. So here we will not obtain the crank rocker or the double rocker mechanism. We will only obtain the double crank mechanism whichever link is fixed. Corresponding to whichever link is fixed, we will obtain the double crank mechanism. And please note that in a mechanism, it does not depend on which link is taken as input link or the output link. Always remember S is the shortest link and L is the longest link, and whereas P and Q are the intermediate links. Now in this we are getting one more linkage, that is deltoid linkage. And in the deltoid linkage, this is S, this is S, this is L, this is L. If S is fixed, then it will form a double crank mechanism, and if L is fixed, we will obtain a crank rocker mechanism. So we have to remember this thing. These are very, very important things, and we definitely need to have a remembrance of these things. Now, for example, if S plus L becomes greater than P plus Q, if this happens, then first of all, law is not satisfied. Which law are we talking about? We are talking about the Grasshoff's law. This law is not satisfied. And always, whichever link you fix, it will always be a double rocker mechanism. It will always be a double rocker mechanism. So if the law is not holding, so on fixing any of the links, we would obtain the double rocker mechanism. Okay. Now we will talk about some practical applications of 4-bar mechanism, and first practical application is the beam engine. We have the बीम इंजन. जैसे मान लीजिए एक टेलर होता है, टेलर जो स्विंग मशीन यूज करता है वो नीचे पैर ऐसे ऐसे करता रहता है, ठीक है. तो एक्चुअली देयर वी आर हैविंग रोटेशन एंड ऑसिलेशन आर बीइंग इंटर कन्वर्टेड. ऑसिलेट, वो जो हमारा नीचे पैर से जब वो ऐसे करता है तो वो ऐसे ऐसे ऑसिलेट होता रहता है, वेयरएज हमारा जो व्हील है वो रोटेट भी करता है. तो हियर वी आर गेटिंग कन्वर्जन बिटवीन रोटेशन एंड ऑसिलेशन. So example, we can write Taylor's swing machine. Taylor's swing machine. The second is the coupling rod of locomotive. Coupling rod of locomotive. Now, in case of the coupling rod of locomotive, we are actually getting the parallelogram linkage. We are actually getting the parallelogram linkage, and therefore it will always form the double crank mechanism. It always forms the double crank mechanism. One is the trailing wheel. In case of the locomotive, we have one trailing wheel and one is the driving wheel. Now we come to another important type of mechanism, that is single slider crank mechanism. Single slider crank mechanism. In case of the single slider crank mechanism, we are having 4 links in total, out of which the 3 are turning pair and 1 is the sliding pair. So we also have to remember that in the single slider crank mechanism there are total 4 links. Out of the 4, 3 are turning pair and 1 is the sliding pair. Whereas in the 4-bar mechanisms we had 4 turning pairs turning about this point, this point, this point and this point. So this is the diagram of a single slider crank mechanism which are having total 4 links, 1, 2, 3, 4. 1 is the grounded link. This is actually the piston or the slider. This is the piston or slider. This is actually the piston rod is also here. Actually I have not drawn the piston rod separately. This is the cross head. Okay, this is the crank. This is the connecting rod. This is the connecting rod. Now in total we are having 4 links. Out of the 4 links, 3 are the turning pair, 1, 2 and 3, and 1 is the sliding pair. Piston rod, cross head and piston are actually considered as one link. We have considered piston rod, cross head and piston are considered as one link. They all are considered as one link. We are not treating them as separate links. Now, if this is fixed, first of all, in order to make it as an inversion, the first inversion is cylinder is fixed. If we fix the cylinder, now if the cylinder is fixed, actually what is happening is rotation is converted into reciprocation. Rotation is converted into reciprocation. Now, and we see here that the shortest link is the crank. Obviously the shortest link is called as the crank, and crank is the shortest link in the single slider crank mechanism. Now, if this has actually two possibilities. The first is the reciprocating engine, and the second one is reciprocating compressor. Okay, if the input is given at the crank, अगर हम crank पर input देंगे, then it would become a reciprocating compressor, and if the input is given here at the piston, then it becomes a reciprocating engine. So it can be both, it can work both as an engine as well as a compressor. So the first inversion was when the cylinder was fixed. Now the second inversion that we will obtain is by fixing the crank. Crank is fixed. Okay, now if this rod, that was the crank, is fixed, then there are two important, that is Whitworth quick return motion mechanism. I am writing QRMMs, it simply means quick return motion mechanism, and the second one is rotary internal combustion engine mechanism. Actually, both these mechanisms have become outdated. I am putting a star because all these they have become outdated. The third inversion that can be obtained here is by fixing the connecting rod, and the inversions of the by fixing the connecting rod are very, very important, and we have to pay attention towards them. Connecting rod is fixed. Now what happens is connecting rod is fixed. Now when the connecting rod is fixed, we are going to obtain two important inversions, that is crank and slotted lever. Crank and slotted lever quick return motion mechanism, and the next one is the oscillation cylinder engine mechanism. The two mechanisms which are obtained by fixing the connecting rod are crank and slotted lever quick return motion mechanism and oscillation cylinder engine mechanism, and these are actually used in shaper and slaughter machines. Shaper and slaughter machines में हम इन्हें use करते हैं. The fourth inversion which is obtained is when the slider is fixed, slider or piston is fixed, and this inversion is called as the hand pump. This is called as the hand pump or bull engine. This is also called as the hand pump or the bull engine. So the inversions of connecting rod are most important, that is the crank and slotted lever quick return motion mechanism, and another one is the oscillation cylinder engine mechanism, whereas the inversions of the crank are Whitworth quick return motion mechanism and rotary internal engine mechanism. These are outdated, whereas these two are taken into consideration and they are widely used. And the inversion of the slider is actually called as the hand pump or the bull engine. Now we will discuss about the very important inversion of the connecting rod, that is the crank and slotted lever quick return motion mechanism. It is obtained by the inversion of connecting rod. Now the name itself suggests that it is quick return, so the time required for the return stroke would be very, very less, and there is no machining. There is no machining in return stroke. And why? In order to save time. मतलब इसका मोशन ऐसा होता है घर्र घच इस टाइप का, मतलब सिर्फ फॉरवर्ड स्ट्रोक में मशीनिंग होगी, बैकवर्ड स्ट्रोक या रिटर्न स्ट्रोक में हम मशीनिंग नहीं करेंगे. नाउ वी विल सी द डायग्राम. नाउ दिस इज द डायग्राम ऑफ द crank and slotted lever quick return motion mechanism, and we have seen that cutting is there in the forward stroke, whereas the return stroke is also called as the idle stroke. And this type of mechanism is actually the crank rocker mechanism. It is crank rocker mechanism because the slotted bar, this is called as the slotted bar, it is actually undergoing oscillation, okay, whereas one of the links is going under rotation, so it is called as the crank rocker mechanism. Now here the ram is attached, and to the ram there is a tool, so and this tool is actually used for machining, and when it is going in this direction it is actually attaining the cutting motion, but whereas for the return motion it is coming out to be idle. Okay, now this is the angle. We are always going to consider only this part for our numerical purpose, so I will draw it separately. This is O, this is A, this is B1, this is B2, and this angle is 90 degree. This angle is actually alpha by 2. This angle is also alpha by 2, and this complete angle is beta. Okay, this complete angle is beta. So this is 90 degree, this is alpha by 2, this becomes 90 minus alpha by 2, and this angle also becomes 90 minus alpha by 2. Now we should remember that the forward stroke is the cutting stroke, whereas the return stroke becomes the idle stroke, and this is R1 R2. This length is R1 R2, and the stroke is actually R1 R2. The stroke is actually the distance R1 R2, which is equals to C1 C2. R1 R2 is actually equal to C1 C2. This is the mid portion, that is 2 times C1 M. C1 C2 is actually 2 times C1 M. C1 is the half, and in the diagram we will observe that the stroke formula can also be written as, 2 into length of slotted lever into length of crank. This is the crank, this is the slotted lever. 2 into length of the slotted lever into the length of the crank whole upon length of connecting rod. This is actually the connecting rod. This was the crank, and this rod is called as the slotted lever or the slotted bar. Beta is called as the cutting stroke angle, and alpha is called as the return stroke angle. The cutting stroke is taking the large amount of time, and therefore beta is greater, and alpha is the return stroke angle, and the return stroke is actually the idle stroke. So if we look here, we will find that this entire angle is alpha, this is beta. So alpha plus beta is equals to 360 degree, because these are the angles at a point. And generally alpha is less than beta in case of the quick return motion mechanism. And we define a term, that is quick return ratio. Quick return ratio is equals to beta upon alpha, and it is always greater than 1. So quick return ratio is equals to beta upon alpha, and it is always greater than 1. However, in the problem, if it is given less than 1, then we will take it as alpha upon beta. Okay, we will take it as alpha upon beta if it is given less than 1. So these are the important formulas, that is the stroke length is equals to 2 into length of the slotted bar into the length of the crank whole upon the length of the connecting rod. So the length of the connecting rod is coming in the denominator. So this is a very important concept that we have to remember, that if the value of the quick return ratio is given greater than 1, then we would take it as beta upon alpha. else it is always taken as, we will take it as alpha upon beta, and normally it is equal to beta upon alpha, and it is always generally greater than 1. Now we would be discussing something about the Whitworth quick return motion mechanism, and if there is any eccentricity in this case, please remember that if E is the amount of eccentricity which is given to the crank and slotted lever quick return motion mechanism, E is the eccentricity which has been given in the case of crank and slotted lever quick return motion mechanism, then we would find phi, which is the angle, such that it is equals to cos inverse E upon L plus R minus cos inverse E upon L minus R, where E is the eccentricity, R is the radius of the crank or the length of the crank, and L is the length of the connecting rod, such that beta upon alpha, that is the quick return ratio, it is equals to 180 plus phi upon 180 minus phi. This numerical data you have to remember. Okay, this is a very important case if E is the amount of eccentricity which has been given. Now we shall be discussing one more thing which is very important from the point of view, and if we are asked about the maximum velocity of cutting to the maximum velocity of return, then this would be equals to C minus R upon C plus R, where R is the radius of the crank and C is the length of the connecting rod. So we also have to remember this formula. So maximum velocity of cutting to the maximum velocity of return is equals to C minus R upon C plus R, where R is the radius of the crank and C is the length of the connecting rod, a distance between the centers भी हम इसे कह सकते हैं. और stroke का formula हमें याद रखना है 2 into length of the crank into length of the slotted bar upon the length of the connecting rod. So with this we come to the end of this lecture. In the next lecture we shall be continuing from here onwards. वी होप कि आपको हमारे लेक्चर्स पसंद आ रहे हैं. हमारे चैनल को दूसरों को भी बताइए सब्सक्राइब करने के लिए, बिकॉज हमारे चैनल पे एवरीथिंग इज अवेलेबल एब्सोल्युटली फॉर फ्री. सारा स्टडी मटेरियल, सारे क्वालिटी वीडियो लेक्चर्स वी आर एब्सोल्युटली प्रोवाइडिंग यू फ्री. सो आप इसका पूरा बेनिफिट उठाइए और अपने एसएससी, जेई, गेट, पब्लिक सेक्टर्स और ईएससी के लिए हमारे साथ प्रिपरेशन करते रहिए. आप अपनी प्रॉब्लम्स हमारे चैनल पे भी शेयर कर सकते हैं या हमारे फेसबुक चैनल पर भी उसे बता सकते हैं. सो फॉर टुडे, थैंक यू.